So a net electric field calculation is again very similar to a net gravitational field calculation, except the advantage when you're doing electric fields is these things are so small and they tend to arrange themselves in crystal structures that we end up with some pretty simple geometry, like a moon and a planet and another planet can be arranged at any distance, and they can have any mass, and they can have any angle separating their locations. But with bits this big, their charge is always some number of the basic charge, and they usually line themselves up on the vertices of squares or triangles or hexagons, etc. So you can make a few assumptions about the angles that are available to you, and you don't have to do quite so much trigonometry in order to figure out all the distances. So I have here an example for you. I have a proton and two electrons arranged on the corners of a square whose lengths are 1 × 10⁻⁻⁻⁻⁻⁻. meters. And I just want to work out the net electric field down at this particular location. So I've got 3 particles, and I'm going to have to figure out each one of them, their contributions. So in order to do fields, you take your force equation, which is K Q1 Q2 over R squared in the R hat direction. And you take one of those charges, the imaginary charge that's going to be there, and I just put it in my pocket for a minute. So this changes this from a force to a field. Let me make that a curly E with a vector over top of it. So I'm going to try and work this out for the electrons. So if I were to work on this, the magnitude of this thing, so the size of it, would be 9 × 10⁹. The charge on these electrons is 1.6 × 10⁻⁹, and the separation between them is 1 × 10⁻⁻10 squared. So if I work that out with the calculator, which I have on me this time, 1 × 10⁻⁻10, put that in the denominator, square it, times 9 × 10⁹, times the charge of that electron gives me 1.44 times 10⁻11. Okay, now this should have been a force, so it should have been in newtons, but I took away a factor of coulombs when I removed one of those charges, so the unit for that field is going to be newtons per coulomb. The same way that the gravitational field was newtons per kilogram. Now newtons per kilogram reduced nicely to meters per second squared, so you could interpret that as an acceleration. This is not quite there because I haven't removed the factor of mass. Okay, but I've got my number. So I can assign these people some names so we know what we're talking about here. This can be Bill, and then Louise, and then how about Jim? Okay, so the electric field contribution from Jim is going to be 1.44 × 10⁻11. But from this point, it's vertical, directly above or below. So I don't have any horizontal contribution, so I can put that in as 0. My vertical contribution is 1.44 × 10⁻11. And here's where you need to be a little careful about your interpretations. R hat is the radial direction. So Jim's radial direction, as far as this is concerned, is pointing that way. But Jim has a negative charge. So if I put a negative charge in here, it's going to reverse that vector. the way you keep this in your brain is that electric fields come out of positives and into negatives. So if I'm standing here and I'm asking about Jim's field contribution is going into Jim, which happens to be in the up direction as I've drawn this diagram. So I'm going to call that positive 1.44 times 10 to the 11 up. I already have the size for Bill, so I can work that out. The electric field for Bill. Bill happens to be directly to the left, so there's only horizontal contributions, so I can label the vertical part as 0. It's going to be this strong, 1.44 times 10 to the 11. And if I'm standing here, the field contribution from Bill is pointing that way, into Bill. Well, that's headed to the left, and just as convention, we've sort of accepted that left should be negative, much to the horror of all the lefties out there. I feel you. It's a burden. Okay, so we've got those two contributions. I just need to get the Lois. I think I was going to write Louise there and forgot a U. Doesn't matter. You can see it's been a long year. I'm a little tired. Sort of lost my mind. Anyway, in order to get Louise's contribution, I'm going to have to do this. But unfortunately, there is no radius. Right? There's no separation between Lois and this point labeled on that particular square. So I'm going to get rid of these. I'm going to have to do a little bit of geometry. So first off, I'm going to draw it just so I can see what's going on. Wow. There we go. So that's the separation I'm after. And now that it's on there, I hope you can see a right angled triangle. So this distance is really just the hypotenuse of this right angled triangle here. So I'm going to need some Pythagorean theorem. That separation will be the square root of this side, 10 to the negative 10 squared, plus this side squared. And if you go and you calculate that out, square this, square that, add them together, you're going to end up with root 2 times 10 to the negative 10, which is approximately 1.414 times 10 to the negative 10. Okay, so I've got a radius now, and I have the charge of Lois, so I can dump all that stuff in and get the net electric field. So let me do that here. Electric field for Lois. Now it says Eloise. You can tell I'm tired because that's not funny. Okay, 9 times 10 to the 9. Q, 1.6 times 10 to the negative 19. Separation, well, I'm going to write it this way. Root 2 times 10 to the negative 10. Because I just have to square it anyway. 9 times 16 is 90, and 36 is, what's 9 times 6 is 54. 54 and 90 would be 144. So this thing is going to be 14.4 times 10 to the negative 10. And root 2 squared is 2. 10 to the negative 10 squared is 10 to the negative 20. .4 divided by 2 would be 7.2. And 10 to the negative 10 divided by 10 to the negative 20 is 10 to the 10. So I get a number that is in the 10 to the 10 range, which is good, because these things were 10 to the 11s. So they're in the same neighborhood. This is further away, so I was expecting it to be less. So that's encouraging. In the r hat direction. Now, for this one, the r hat direction from Louise, keep in mind that electric fields come out of positives, so it is going this way. It's going down and it's going to the right. So I have a horizontal and a vertical component. So I'm going to need an angle. Fortunately, a 1, 1, root 2 triangle is a 45-degree triangle. Pi over 4, of course, if you've taken advanced functions, and calculus and degrees are now beneath you. But we'll just leave it as 45 degrees so we don't scare anybody. If I set it up like this, the horizontal component is adjacent, so that's going to be my cosine. The vertical component is opposite, so that's going to be sine. So the contribution from Lois then, Lois with an E, is going to be 7.2 times 10 to the 10 cos 45 horizontally, sine 45 vertically. And since the field is coming out of Lois at that point, it's going to the right, so that should be positive, and down, so that should be negative. Okay, so I'm just going to throw that in here, and I will write it up here as a combined bracket. So 7.2 times 10 to the 10 multiplied by cos 45 gives me positive 3.782 times 10 to the 10. And since sine 45 and cos 45 return exactly the same value, I can say that the vertical part will be negative because of my negative. 3.782 times 10 to the 10. So I can get rid of this stuff in order to get my total electric field. So in order to get the net, I just need to take Jim's contributions and Bill's contributions and Lois's contributions and stack them all on top of each other, the same way as you did with gravity problems. So 3.782 times 10 to the 10 subtract 1.44 times 10 to the 11 gives me negative 1.061 times 10 to the 11. And 1.44 times 10 to the 11 subtract 3.782 times 10 to the 10 is going to give me exactly the same number. No, it's not. It's going to make it positive. Okay. So I have a net electric field that is headed to the right. Hold on. 0.44. Okay, got it. I have a net electric field that is headed to the left and headed up. So the net electric field is going to be headed that way. So if I were to erase this pink line then, my E net is pointed that way. And since my horizontal and vertical are the same, then this will be 45 degrees from horizontal or vertical, however you want to measure it. Okay, so it would be nice anytime you give a vector that's given in x and y components to combine them to get a magnitude. So the magnitude of this thing square this, add them together, square root. It's just Pythagorean Theorem. Square that, double it, square root it. .062 times 10 to the 11 gives me 1.502 times 10 to the 11 newtons per coulomb. Let's call that towards the center of the square. And I'll write that right on my face. Center of the square. Okay, lovely. So now that I've got the size of the force and I have the direction that it's, the electric field, I can use that then to put in a test charge. So what would the force be? So calculate force. Calculate the force on an electron placed at that point. Electrons. These markers are as tired as I am. Placed at that point. Okay, so I'm going to put an electron here. Well, maybe you remember from the beginning that I got this electric field by taking the force equation and ripping a charge out of that. So this is going to be true then. If I put the charge back in, I get force. So the force this thing is going to experience would be 1.502 times 10 to the 11 multiplied by the charge on an electron, which is negative 1.6 times 10 to the negative 19. Notice that I put that negative back in, even though I've been chirping about not using it this whole time. And I end up with that times 1.6 times 10 to the negative 19 gives me negative 2.403 times 10 to the negative 8 newtons. Okay, so why did I put that negative in there? Well, I'm going to erase this so it's not on my face, but it does say that the field is pointing towards the center of the square, and I have a negative here. So that negative means it is not pointing towards the center of the square. Well, which direction would that be? Well, directly opposite of this direction would be going this way. So if I took an electron and I put it at that particular spot, it's going to experience a force of 2.403 times 10 to the negative 8 newtons in that direction. So I basically built myself an electron cannon. Right? If I were to put charges there, they get blasted away from this particular arrangement. Now you've come across electron cannons in your time. Actually, maybe you haven't. I certainly did. If you've ever seen a giant TV, like the glass tube kinds, you maybe have to go watch some 90s sitcoms in order to see one of those. They operated by blasting an electron stream at pixels on the screen in order to light them up. So in the back of those tubes is an arrangement something like this. Right? There's negative charges around here, and then you have an electron source that would drop them into this particular location. You get like a hot wire, right? Something that the electrons are easy to eject. And these charges here, which would be arranged in a ring, so there's not just two, there's many, just blast the electrons off of there, and you get this nice little electron gun happening in the back of your TV, which you can use to light up all the pixels, which is kind of cool. Whew. So that's just an example of a square. The problem sets have a triangle, which you should be able to handle. They have a square, which you should be able to handle because you've seen it. There's a hexagon, which is a little more challenging, so give it a try. And if you get stumped on it, don't panic, because it's a geometry problem that makes it complicated, not the physics of it. So as long as you can handle the triangle or square, you're good. And then just to be cruel, I put in a pentagon, which you have to do a whole bunch of math on in order to get these radii and the angles. So if you're up for a challenge, and if you want some practice before the exam for those gravitational field questions, it would be an excellent exercise. So with that, I will say good luck.